All right, so this is class number 6. I got a question from a student yesterday who was struggling to find my lectures on YouTube, you know, the ones that are posted there. So I'd take a moment to just show you how to get at those. There's a link in our class page that would take you to my channel. All right, and then once you get there, the videos are listed chronologically. Here, if you click on videos, then it's just this is the most recent one, and that's the one before that, and so on and so forth. So this is in chronological order, and you could get to it that way. Or if you click on this, then you could search by like the class meeting. So if you did 318 class 5, it would bring up all of the 318 class 5s I've ever done. So here we go, from a day ago, from 4 years ago, and so on. So just in case you want to review these class meetings, they are posted online. And so remember, we're working in chapter 3 of the textbook, and the other thing that I think is important for you to be doing is reviewing what the author has written about the material, because there's a different point of view and sometimes different illustrations and examples that can help to clarify concepts that otherwise maybe I'm not able to address in the same depth. Your next assignment isn't due until Tuesday the 21st, so that's a pretty long gap there. It's in part because now we've switched over some new material. But I'd encourage you to get an early start on this. We went over some calculations in the lab on Tuesday, talking about depth to the centroid and center of pressure, just introducing those concepts. And that stuff comes into play in this homework 3. So maybe the earlier you get looking at this homework assignment, the better, especially because if you look at the homework problem, then you'll be able to see the examples from the perspective of, oh, I need to know this because it fits into the homework assignment. So I'm not saying you necessarily need to finish it real soon because you've got quite some time before it's due, but definitely have a look. Now today we're going to continue talking about ways to measure pressure. We talked about piezometers on Tuesday. So we'll talk about other more realistic methods of measuring pressure today with manometers, and then we'll also spend time talking about variation of pressure within the atmosphere. Any questions about announcements or just anything general course related? I do have a grader hired now, and the grader is going to be going through your assignments real soon. So homework 1 probably graded this evening, and homework 2 over the weekend. So you'll start to get feedback, and you'll see the grades in the grade book. And in addition to the score, you'll also have comments that shows you how many points were deducted for which problem when you've made mistakes. And the grader's going to try to give you a little bit of information on maybe what you did wrong if there's an error. I think the grader's going to do a great job. It's a really conscientious student who I really trust. But if you feel like somehow there's been a misunderstanding or you were somehow shortchanged on points you should have gotten, just let me know, because ultimately I'm responsible for making sure that your work is graded fairly. So if there's a problem, don't just stew about it. Just let me know and I'll take a second look. That said, it's also great when people aren't like grubbing for half a point here and there. Ultimately it's not going to matter. So like if it matters, let's get it fixed. But I'm not saying that as an invitation because I want to nitpick over tiny little increments. All right, manometers. Now, who can remember when it comes to a piezometer? Let me just sketch a piezometer on the whiteboard here. Let's say we had a pipe and there's water flowing through the pipe and it's pressurized. And so one way of measuring the pressure is you just cut a hole and water spraying out all over the place. But then instead of allowing the water to spray out everywhere, what you do is you put this vertical conduit, and then the water level rises to a certain height. And it is measuring the pressure in the pipe because there's delta H involved. And even though water's flowing through the pipe, water is not flowing inside of this vertical piezometer. Inside the piezometer, conditions are static, meaning the water isn't flowing. The water rose to a certain level, and then it stopped. And because it's static, we can say that delta P is delta H times gamma, being the unit weight of the fluid. So that's our simplest way of measuring pressures with a piezometer. So who can remember what are some of the impractical issues with measuring pressure with a piezometer? Yeah.
How high the height is.
Okay, so how high the height is. Yeah, we talked about how, it'd be like 90 meters if you're going to measure water pressure in a municipal network. And so you'd have to have really tall stilts or maybe fly around with a helicopter or a drone to see what the liquid level is at. So that's a problem, is the vertical deflection is really large. And also what? There was one more impractical issue. Exactly. It doesn't work for gases because the gas would just go right out of the top of the tube. It works okay for liquids, although, there's a contamination issue. Like what if a bird was flying over this open tube, You wouldn't want that to be open to the atmosphere, but it's useless for gases. So, a U-tube, this is different from U-tube that we were looking at before. This is called a U-tube because it's a U-shaped tube. This is a manometer that avoids both of those limitations in a piezometer. And so what it does is it uses a different liquid than what's flowing through the pipe. And in fact, I shouldn't say liquid, a different fluid. Because you could have a liquid or a gas flowing through the pipe, but then you use some other manometer liquid. And the advantage of having a separate manometer liquid is you could choose something that's really dense. And so if you're choosing a really dense fluid, then the delta H doesn't have to be as big as it would with water. So then that avoids the issue of having like 90 meters of deflection. If you're using mercury, which is mercury, so the specific gravity of mercury is 13.56. So what that means is mercury is 13.56 times as dense as water. Or the density of mercury is 13,560 kilograms per cubic meter. It's really heavy per unit volume. So if you use mercury as the manometer liquid, then you'd only have 1/13 the deflection that you'd see with an ordinary fluid like water. So that cuts down on that issue of having to have a really long tube. Then the other advantage of having a separate manometer liquid is that you could have a liquid in the U-tube, but then a gas flowing through the pipe. And so the liquid would act as like a seal or a stopper, so that there wouldn't be any exchange between the gas in the pipe and the gas in the atmosphere surrounding the pipe. So it would be a barrier. So from a problem-solving standpoint, the way that we use U-tube manometers to determine the pressure inside the pipe is we start where we know something. And it's the same thing that we did with those multi-liquid problems, where I said the strategy there is you start at the surface because you know the pressure at the surface is zero gauge pressure. And then you work downward, fluid by fluid, one layer at a time, towards the unknown. And the same thing applies here. You start at location 1 because you know the pressure of the liquid right at the top of that U-tube is the same thing as the pressure of the atmosphere. So at location 1, it's atmospheric pressure. So like if we're in absolute terms, then it would be 101,325 pascals. If we're thinking in gauge terms, we just say the pressure is 0 here at this interface between the gas and the liquid. And then we go from 1 down to 2. Now, why is 2 there? Well, it's because there's a layer on the other side of the U-tube. And so we just say we're going to go vertically down until a point at which there would be a transition somewhere in the U-tube. So on the other side of the U-tube is the barrier between this fluid that's going through the pipe and the manometer liquid. So there's 2 at the same elevation as this 3 on the other side. Now, the pressure increases as you go down. So P2 is greater than P1. We kind of get that by now. We've been looking at enough of these that we know the pressure is going to be larger as you go down. And then the flip side of that is when you go up through a fluid, the pressure is decreasing. So P4 is less than P3. So this is really just an accounting problem where anytime you're going down through a fluid, you start at what was the previous pressure and you add some amount. And then anytime you're going up through a fluid, you start at what was the last pressure that I knew at some sort of an interface between different fluids. And as you're going up, the pressure decreases. So just as an illustration, let me give you the calculations on this one. What if we had a delta H is 45 centimeters and L is 183 centimeters? Well, the first things we need to do is change from units of centimeters to meters. I'll always be giving you the wrong units just so you get in the habit of double checking to make sure what it actually needs to be. And sometimes I'll give you useless information that you don't need just to give you practice of ignoring the things that don't apply. Because honestly, when you're out in the real world, getting information from clients or information from your boss, most of the things that people will tell you doesn't necessarily even apply to the situation. All right, so let's say we want to start at location 1. So we're going to find the pressure at the center of the pipe. And what we're going to do is we're going to say P1 is 0. We'll calculate this in gauge. The pressure is 0. And then let's do some of these preliminary calculations. The unit weight of water, because it's saying that water is flowing through the pipe. So let's use 9810 newtons per meter cubed as our unit weight of water. And then the unit weight of mercury, this is rounded off to 13.6. I told you earlier it's 13.56, but that's all right. We'll go with it. 13.6 times 9810 newtons per meter cubed. So our unit weight of the manometer is 133,416 newtons per meter cubed. Okay? So P1 is 0. What is P2? P2 is P1 plus delta P from 1 to 2. So it's however much pressure there was at location 1 and then plus the pressure the rest of the way. Let me just draw a little sketch here so that we'll have it available as a reference. Here's my U-tube going in a U shape. Here's 1, 2, and here's this layer. It's a different fluid, 3. And finally, we're going up to 4. And so the delta H is 45 centimeters. And then it's 183 centimeters from 3 to 4. Sorry for the delay, just pulling up my solutions so that I can include this in the recording. One of these days I'll figure out how to use the pen on the screen here, but I just have such terrible handwriting. I feel it would do more harm than good. All right, here we go. This is the one. All right, so P2 is P1 plus the change in pressure between 1 and 2. So that is 0 plus the delta H, which is 45 centimeters, so 0.45 meters. and then I have to use the unit weight of the fluid that I'm going through. And it's this mercury manometer fluid, so I'm going to use the unit weight of the very dense mercury, 133,416 newtons per meter cubed. And that is 60,037 pascals. So that's the pressure here at location 2. Now, as I go down through the U-tube, the pressure is increasing. When I go sideways, nothing is happening. When I go back up again, it's decreasing. Since 2 and 3 at the same elevation, and they're connected by the same fluid, they have the same pressure. So P3 equals P2, which is 60,037 pascals. Now, you have to be cautious though. 2 and 3 are the same pressure because they're at the same elevation and through the same fluid. If I extended this line over from 1, it's not the same pressure over here in the opposite leg aside from 1, because if I go between them, I'm going through different fluids because there's this barrier here between the mercury and the water. So it's only the same pressure at the same elevation if you're going through the same fluid to get between them. If there's a secondary fluid between them, it's not the same pressure. All right. Now, P4 is what? What is the pressure at location 4?
Change in P minus P3.
Good. That's right. So it's the negative of the change in pressure. Maybe we should just say it's the pressure at 3 minus delta P between 3 and 4. Because we're going up through the fluid, the pressure is decreasing. So the pressure at location 4, which is in the center of the pipe, is 60,037 pascals minus 1.83 meters of water, 9810 newtons per meter cubed. And so the change, that part of it is 17,000, oh, let me scroll down. 17,952 pascals. That's how much pressure is lost as we go up through 1.83 meters of water. So the final P4 is 42,085. 42,085 pascals. So that's basically 42.1 kPa. That's the gauge pressure at the center of the pipe. It's just a counting, right? And if there had been multiple fluid layers, then we could continue this process going up and down as we work from the known towards the unknown. One thing I'm going to point out, what's the equation that we're applying to solve these problems? What's it called, the name of it? Hydrostatic equation. Yeah. So the hydrostatic equation applies in the U-tube because there isn't any water flowing through the U-tube. Technically, the hydrostatic equation isn't what applies when you have flowing water. So if this is a pipe, like this big one up above, if there's water flowing through this pipe, we really shouldn't be applying the hydrostatic equation from this part up to there. I mean, it's still true that the pressure is going to be decreasing as you go up through the pipe, and it's okay-ish to apply the hydrostatic equation vertically in a pipe, but you couldn't apply it if you were moving horizontally. Because when you're moving horizontally, like in the direction of flow, that's when the effects of pipe friction really kick in. So it's probably okay for us to say that between 3 and the center of the pipe, it's probably okay to use the hydrostatic equation, but it's not perfect in the same way that it is perfect to apply it in this part of the tube where conditions truly are static. So I just wanted to make you aware that we're on a little bit thinner ice when we go from the opening of that tube, which is, inside the tube, the water's not moving, but then as soon as you go outside of the static U-tube and into this environment where the water's swirling past, the pressure change might be slightly different than what's described by the hydrostatic equation. All right. Any questions on this example? All right, well, you're going to get some practice with this one. It's so tricky because we've got a layer of water and then a layer of mercury and then some oil, finally another layer of water, and we want to find out what is the pressure here at location A. All right, so you're just going to be applying successively, serially, over and over, this notion of delta P is delta H times gamma. And just so that we standardize our approach, let me label the interfaces for you. So let's go with 1 being the interface of air and water, 2 being the interface of the water-mercury, 3 being down here where the mercury and the oil come into contact, up and over the bend, to 4, which is the interface of oil and water, and then finally here's location A, which is I want you to find the pressure at A starting with P1 is 0. So P1 is what, P2 is what. You're going to go row by row and answer all of these questions until you get down to location A and find the pressure there. The dimensions here are intentionally a little bit tricky. I mean, everything you need is given, but you got to maybe look at it for a second before you really see what are all of the heights that apply. So you can assume that this 30 centimeter dimension extends over and it's the same elevation as this line. These two lines are on the same horizontal plane. All right. I'm going to pause for a moment. I'll circulate around with the solutions, and what I'd love is if you scoot together with your classmate and work through this one together. All right, so let's look at this tricky manometer, and what makes it tricky in part is the dimensions. So it's 0.9 meters from 1 to 2, then it's 0.6 meters from 2 to 3. From 3 to 4 is 1.8 meters because it's the 30 centimeters to get from the interface up to this line and then 150 centimeters up. And then from 4 to A is 1.5 meters. So the distance is one aspect of it that makes it tricky. All right, so we do these preliminary calculations off to the side here to get our unit weights that are going to apply. Water, 9810, oil, 80% of that, mercury, 13.6 times the unit weight of water. So we have those calculated and available for when they're needed. And starting at 0 pressure at 1, we go down through the fluid and are adding pressure. So the change is 8829 pascals, and added to 0, that just means the pressure at location 2 is 8829 pascals. Then we're going down through the mercury, which is the heavy stuff. The pressure accumulates quickly through the mercury because we have this large unit weight. So it's the starting pressure at location 2 plus the change. And you can see what I've done. So I've got this bracket here just to kind of visualize what's the magnitude of the product of the elevation and the unit weight. And that way, when I double check my calculations later on, I can just see the pieces as they fit together. So the pressure at 3 is 88,878. Pressure at 4, since we're going to go up through the fluid from 3 to 4, is a minus. So it's P3 minus the delta P. And so this time we're going through oil. We use the oil unit weight. So the pressure is going to decrease at a slower rate than if we were going through oil or through water or mercury. So 74,752 is the pressure at 4. And then finally, we've just got one more step remaining to get us down to location A. It is the pressure at 4 plus, because we're going down again through 1.5 meters of water. And the pressure change that's equivalent to 1.5 meters of water depth is 14,715 pascals. So you can kind of see why they sometimes talk about a pressure in terms of a depth of a fluid. Sometimes some gauges will say, it'll read out the pressure in terms of millimeters of mercury or inches of water or whatever. And they're just talking about the pressure magnitude that's equal to that depth of the fluid that's indicated. So here, 1.5 meters of water is a pressure of 14,715 pascals. If we add that to the pressure that there was at 4, then the final answer here is it should be 89.5 kilopascals at the pressure at the center of the pipe. Okay. Any questions before we move on from this example? So now you really got to start on the homework, right? If you've got a couple of easy problems like this, just get them out of the way and then you can just forget the stuff. And then have to relearn it again as you cramp for the test, I guess. But if you get it done early, then at least it'll still be fresh in your mind. Let's talk about a differential manometer. This is a little bit of an evolution compared to the U-tube. The U-tube was open to the atmosphere. So this U-tube was measuring what's the difference in pressure between the atmosphere and the pipe where the tube is connected. That's what this was telling you. The deflection, delta H, indicated a pressure change between the atmosphere and what's in the pipe. But if we evolve a little bit and we connect the other end of the tube to some other location on the pipe, then the differential manometer expresses the change in pressure between these two locations on the pipe. So we've got location 1 and location 2, which is downstream. The water is flowing, or whatever the fluid is flowing from the left to the right. And notice this pipe is horizontally oriented, and that's significant. It simplifies things a little bit if it's horizontally oriented. In a moment, we'll look at what if the pipe is inclined. But if it is horizontal, then you can calculate the change in pressure between location 1 and location 2. It's just delta H, the deflection, multiplied by the difference in unit weight between the manometer fluid and whatever this fluid is that's flowing through the pipe and is the other thing in the tube. So if it's horizontal, that means that the elevation at location 1 and 2 is the same. It's just wherever you're tapping into this pipe with the differential manometer is at the same elevation. If that's the case, that tells you the difference in pressure. Does anybody remember? Okay, so where is the pressure higher? First of all, at 1 or at 2? Which is experiencing a greater pressure? 1. You are correct. And how did you know? What was the indication that there was more pressure at 1? The fluid is pushed further towards 2. That's right. I mean, think about, something's pressing down on one side. It's kind of like a teeter-totter, You press on one side of it and the other side goes up. So here, there's more pressure on the left side of the U-shaped tube than on the right. And that's what's causing the deflection, is because there's more pressure over here on the left side. Now, so that is telling us which has more pressure, 1 versus 2. Now think about, why is there more pressure at 1 than 2? Or maybe another way of saying it is, why is there less pressure downstream at that location 2 than there is upstream? Pipe friction. Correct. As water flows through a pipe, energy is lost in the direction of flow because of the effect of pipe friction. and quantifying how quickly, like the rate that energy is lost as water flows through a pipe, that's a tricky, fun thing that we get to do later. But for now, just keep in mind that it's because of pipe friction that the pressure decreases in the direction of flow. And so that's what this is measuring. This is telling you the change in pressure that's caused by pipe friction, and the way that you'd quantify it is with the deflection of what's in the differential manometer. Now, more generally, I even bolded this. That's a new addition. See, these notes are always evolving. I made this bold this morning. More generally, this equation is true even if the pipe is inclined. So P sub z is something I've defined for you before. It's the piezometric pressure. Piezometric pressure has two terms. Piezometric pressure is pressure plus z times the unit weight. Let me write that on the whiteboard here, just so we see it in front of us. P sub z is P plus gamma z. Piezometric pressure tracks two things. It tracks what is the pressure at this location, and also at this location, what is our elevation above a datum that we're measuring all of our elevations against. And what I told you before about piezometric pressure was that inside of a tank, for example, if we have two locations in a tank, that although the pressure is higher at location 2, if we go down through a fluid, the pressure increases, but you're losing Z. And so although P1 is less than P2, or another way of saying that is P2 is greater than P1 because it's deeper in the fluid, P sub Z1 equals P sub Z2. The piezometric pressure is the same because piezometric pressure keeps track of both the pressure at a location and its elevation above the datum. So that's what you were told previously about piezometric pressure. So now what I'm saying over here is that the change in piezometric pressure is what's measured by a differential manometer. And at horizontal case, where Z1 equals Z2, is just that the elevations cancel each other out. So P sub Z1 is like saying P1 plus gamma Z1. So this is P sub Z1 minus P1 plus gamma, P2 plus gamma Z2. So this is minus P sub Z2 is equal to delta H times the unit weight of the manometer fluid minus the unit weight of whatever the other fluid is that's going through the pipe. So when it was horizontal, Z1 equals Z2, and so that's why this equation applies if it's horizontal, is because Z1 and Z2 are equal. But more generally, if we tip the pipe upward, like in this example, the pipe is tipped upward, the differential manometer, it's not just measuring the change in pressure between 1 and 2. It's measuring the change in pressure that's caused by pipe friction. So see this delta H? This delta H is measuring the change in pressure between 1 and 2 that's caused by the fluid flow. Before we get into crunching the numbers here, let's just think about conceptually what's happening in this system. Let's cover some basics before we start doing calculations. Okay, so let me set the stage. Water is flowing through this pipe, but inside of the differential manometer, conditions are static. So it's in an equilibrium inside of this differential tube. The conditions, like the fluid isn't flowing, but the fluid is flowing through the big pipe. So is everybody with me so far? You can kind of see that the water is moving because of those arrows. Gives it away. But let's say, what if we closed down a valve and we stopped the fluid flow? Would there still be a difference in pressure between location 1 and location 2, even if the fluid wasn't flowing? Would there be a pressure difference? I heard somebody say yes, and they're right. So why would there be a difference in pressure between 1 and 2, even if the fluid wasn't flowing? Because there's a difference in elevation. Right. Okay, so if we closed that valve and the fluid stopped flowing, there'd still be a difference in pressure, but there wouldn't be any delta H, because there wouldn't be any reason for a delta H. Even though there's a difference in pressure, the way this works is that the pressure is decreasing at the same rate through the pipe as it is through the manometer tube if there's no fluid flow. So we're going down from 2 to 1. Right? 2 is a higher elevation, 1 is a lower elevation. So whether, like when the valve is closed, if you go to 1 through the pipe, or if you go to 1 through the tube, the manometer tube, the rate of pressure change is the same. You're going downward through the same fluid. So there's no reason why there would be a delta H, a deflection, if the fluid wasn't flowing. Hopefully you're able to convince yourself of that conceptually, but if not, just take it from me that this delta H only arises when the fluid is actually moving through the pipe. So what it's measuring, the delta H, is measuring the effective pipe friction. It's not measuring the pressure effect that's caused by the elevation difference. It's only, this delta H is only measuring the pressure effect that's attributable to pipe friction. All right, so with all of that conceptual stage set, let's go through some calculations now. We have a known pressure at 1. The pressure at 1 is 450 kilopascals. And we want to know what's the pressure at 2, and then also what's the change in piezometric pressure. So I'm going to go through these calculations. I'm going to write them on the board, and we'll discuss it as I do that. All right, so we're going to start where we know something and work towards the unknown. That's a problem-solving strategy I've mentioned on a couple of previous equations. Start where you're given a pressure and work towards the unknown. So P1 is known. So P1 is given as 450 kilopascals. So I'll do the numerical substitutions later. For now, I'm just going to write symbolically what is the pressure at 2 in terms of the pressure at other locations. So P1 plus delta Y times the unit weight of water. Okay, so what did I do there? I said we're starting here at 1, and we're going to go down delta Y through water plus delta H times the unit weight of water. So I'm applying the same kind of manometer thing that we've done before. I was here and I'm going down, so I'm plussing some extra pressure, and then that's telling me the pressure here, which is the same as the pressure there on the other side of the manometer. So now I'm going to go up, so minus delta H times the unit weight of mercury, Hg, minus delta Y times gamma of water, minus delta Z times the unit weight of water, and that is how you get to location 2. So all of that is going to be equal to P2. So what I did was I said P1 plus, because of a pressure change as you're going down, plus some change, minus the delta H times unit weight of mercury, minus through the water, delta Y, and then finally The last thing I do is the change in elevation, the delta Z, to get up to location 2. So I'm applying the hydrostatic equation through the manometer tube, because that's where conditions are static. All right, so now there are a few things that can cancel out, like common terms can cancel out. Like I think I have a delta Y times gamma of water over here. So this was a plus delta Y gamma of water. Here was a minus delta Y gamma of water. So those cancel out. So simplified, it's going to be P1 plus delta H times gamma of water minus delta H times gamma of mercury minus delta Z times gamma of water is equal to P2. So I'm just working my way through the tube using the hydrostatic equation, and now we can do some numerical substitutions. 450,000 pascals plus 0.05 meters of water, 9810 newtons per meter cubed, minus 0.05 meters of mercury, 133, oh, this time I'm calling mercury 133,000 newtons per meter cubed. That was up in the preliminary info there, newtons per meter cubed. Minus 1 meter of water, 9810 newtons per meter cubed, and all of that is what gets me to the pressure at 2. Let me bring this solution up on the screen so that it's included in the video record. All right, now I find it useful and interesting to get a clearer sense of how the pressure is changing through each one of those transition points. And so you can see here that I've found that the first increase in pressure is 490.5 pascals. And then this next change in pressure through the mercury is 6650 pascals. And then finally, this last step upward through the water is 9810 pascals. So if I add it all together, P2 is 434,030 pascals. I guess 0.030.5 pascals. So that's the pressure at location 2. And that's the first part. It's asked, what's the pressure at 2? And so, like, why is the pressure there lower than the pressure at 1? Let me ask you that. 450 is a bigger number than 434. Why is there less pressure at 2?
Because of the elevation.
Okay, elevation change is part of it. So location 2 is at a higher elevation, so there was less pressure because we were moving vertically upward through the fluid. So that's part of it.
Pipe friction.
And pipe friction is the other, because location 2 is downstream. So both of those worked in the same direction. There was less pressure at 2 because of the pipe friction and because of the elevation difference. But think about it. It would have been a little bit more confusing. What if location 2 was lower than location 1? Then it could have been that pressure was increasing because of the elevation difference, while simultaneously decreasing because of the pipe friction effect. So we don't always necessarily know downstream if it's a downhill pipe. You don't know if the pressure is going to be larger or smaller downhill, because it could be that the pressure is decreasing at a faster rate because there's lots of pipe friction. So sometimes you have to actually do the calculations before you know if the pressure downstream is higher or lower. If it's horizontal, pressure downstream is always going to be lower. If it's vertically inclined, the pressure downstream will always be lower. But if it's inclined on a downward slope, it could go either way. Does that make sense? Last part. What is the change in piezometric pressure? Okay, so P sub z, so delta P sub z, according to this formula, P sub z1 minus P sub z2 is 0.05 meters. So that's the deflection of the mercury component there. And then the difference between the manometer fluid and the fluid that's flowing through the pipe. So 133,000 newtons per meter cubed minus 9810 newtons per meter cubed. So the delta P sub z is 6159.5 pascals. So the change in pressure between the 2 points is like, what is that? 16 kilopascals, but it's only 6 kilopascals is the change in piezometric pressure. And the piezometric pressure is telling you how much of the pressure change was due to pipe friction. So remember, part of the pressure change was because of the elevation difference, and part of it was due to the pipe friction. So this P sub z is already taking into account the elevation difference between the 2 points. And so this is how much is due to the effect of the pressure exerting a friction. I think you've got a homework assignment that's like this one too. So you'll make quick work of that. Any questions before we move on to atmospheric pressure variation? Piezometric pressure is what we've just calculated here, where it's pressure plus gamma z. Sometimes later in the semester you'll see the book referring to piezometric head. And piezometric head is just where you divide each term by gamma. And so instead of being units of pascals, piezometric head has units of length, like meters. And so each term is just divided by gamma. So I wanted to put this slide in here for reference later when we do some calculations related to piezometric head. All right, so this is a weather balloon. It's going to be sent upward to collect data that describes the temperature. That's usually what they're after with balloons like this, is to see how warm it is at certain elevations, because that can change from day to day. But you'll notice they're about to launch this balloon, but the balloon continues quite a lot. It's not all the way inflated. And do you know why they don't inflate the balloon all the way? Because it's going to expand because the pressure of the atmosphere aloft is lower. So it's because of the expanding gas. They don't want it to pop. You've probably released balloons before when you were a little kid, and they get high enough and they can pop. They don't want this one to pop. So we're going to be talking about the relationship between temperature and pressure changes as you go upward through the atmosphere. This is a graph that relates the typical lapse rate. The lapse rate is the general relationship between a decrease in pressure that occurs, a decrease in temperature that occurs as you go up through the atmosphere. And what causes this is the fact that as you move up through the atmosphere, there's less pressure. And so temperature, pressure, and elevation are all intimately related. And within the troposphere, there's more or less a linear relationship here, where with each kilometer of elevation you get, you lose 5.87 Kelvin. And the increment, the size of a Kelvin, is the same as the the size of a degree Celsius. Although they have a different 0 point, where water freezes at 0 Celsius but 273 Kelvin. They have a different 0 point, but the size of the degrees is the same. So it's also 5.87 degrees Celsius is lost as you go up through 1 kilometer of elevation. So if you climb a mountain and you go up 1,000 meters on a mountain, then the temperature aloft is going to be about 5.9 degrees Celsius cooler, which is quite a lot. It's definitely noticeable. Now, you could find the temperature at some elevation using this equation. So that tells you the temperature at elevation Z, where alpha is this lapse rate. 5.87 degrees is lost for each kilometer that you go upward. Now, this substituted into this other equation. So the numerator in this pressure equation is simply the temperature at some elevation. So this larger equation on the right-hand side, this is just telling us what is the pressure at some altitude. So the pressure at elevation Z. And so the elevation goes into the temperature formula for the numerator, the temperature up above, and then the exponent you can see here in this equation takes into account both the gravitational acceleration constant, the lapse rate alpha, and then also the gas law constant for air that you can get from table A2. So this equation will allow us to calculate the pressure at a certain elevation that's caused by, the pressure change is caused by the change in temperature of the gas. So just to give you a quick taste of these calculations, did you ever see the Mission Impossible where he was climbing up the side of the Burj Khalifa? It was a good movie. You should watch it if you hadn't. Consider it fluid mechanics homework, all right? No, not really. I've been in the Burj Khalifa a couple of times, and the observation deck that I went to was just barely more than halfway. It's not even like the top deck. I was in kind of like the cheap seats that they don't charge you too much to go to, and man, it feels pretty high. To the very top is 828 meters. So what I'm saying is, let's find out using these methods, if you assume that the temperature at the base of the building is 30 degrees Celsius, and we have this 97,189 pascals, atmospheric pressure can change from day to day. It's not always 101,325 pascals at sea level. So let's just say today, on the day of this example, the pressure at the base of the Burj Khalifa is 97,189 pascals. So what would be the air temperature and the air pressure at the top? Now, unfortunately, we've only got 3 minutes before class is over. So what I would prefer to do is pause and allow you to get the experience of running this in your calculator and acquainting yourself with the formula. But because we had that presentation at the beginning of class, instead what I'm going to do is just show you the calculations, and we'll talk about them, and at least you would have seen them used rather than using them yourself, which would be better. The first thing that we have to do when we're working in gas problems, it's best to convert things over to Kelvin, the temperatures. And so we have 30 degrees Celsius. Let's convert that given temperature of 30 degrees Celsius to Kelvin. So it's 303.15 Kelvin. And alpha is given in terms of degrees per kilometer, but let's convert that into degrees per meter, because in this formula, we're going to be multiplying alpha by a distance in meters. So the delta Z that's in here, it's 828 meters. I mean, I could say it's 0.828 kilometers, and then I could use the alpha in terms of Kelvin per kilometer. But basically, the bottom line is I'm just suggesting we convert alpha over to units of meters. All right, so we've got that done as a preliminary. Looked up the R value for air. from the table A2, 287 joules per kilogram Kelvin. Now, we can calculate the temperature up above. It was, remember, 30 degrees Celsius at the base, which was 303.15. The temperature is cooler, 4.88 degrees cooler up above. And so it's cooling because of the atmospheric expansion. So the temperature aloft is 298.27 Kelvin. And now we substitute that into the formula for pressure. And I've just calculated the entirety of this exponent. If we have G and alpha and R, it's 5.823. It's unitless. All of the units cancel out. That's why R has the units that it does. So with the pressure at the base multiplied by what's inside of the brackets here, which is essentially the ratio of the temperatures, aloft versus at the base, taken to the power, you can see that the pressure up above, 88.4 kilopascals. And so it is, number one, I can tell you from experience, it's noticeably cooler up there. You can feel it. And your ears pop on the way up because of the elevation change and the pressure change. All right, well, that's all the time we have for today. It's 12:15. Just remember that your next assignment's not due for a while, not until the 21st, but maybe getting an early start would be the prudent and wise thing to do. All right, have a good one. I'll see you on Tuesday.